As someone who trains AI architectures for a living, there's one question I get all the time. How does an AI actually learn? Well, today we're diving deep into the single most important algorithm in all of machine learning, backpropagation. This is the secret sauce, the real engine that allows a machine to get smarter, and we're going to break down exactly how it works. It really all comes down to this one simple question. When a machine gets something wrong, and believe me, in the beginning they get a lot wrong, how does it even know what part of it's thinking to fix? How does it make sure it doesn't make that same mistake over and over again? So to answer that, let's do a super quick refresh on what we're dealing with. A neural network is kind of like a digital brain, right? It's this web of interconnected neurons all set up in layers. And the connections between them have these things called weights, which you can just think of as the network's internal settings, like millions of tiny little knobs. Our entire job is to tune all of those knobs perfectly. Okay, so let's see what happens when those knobs are all wrong. We've just shown our network a picture of a handwritten number 2. But look at its output. The network is totally confident. It's screaming that it sees a 7. This isn't a small mistake. It's a huge one. The network is confident, but it's confidently wrong. So now what do we do? This is where the real magic starts. We've got to have a methodical way to trace that big mistake at the end all the way back through the billions of tiny knobs inside the network. We need a way to assign responsibility for the error. And honestly, this is the best phrase I've ever heard to describe backpropagation. It's a chain of blame. The whole point isn't just to know that we were wrong. It's to figure out exactly which connection, which little knob is most to blame for that mistake. Let's make this even simpler. Think about a blindfolded archer. Step 1, the archer shoots an arrow. That's the forward pass, our network making its guess. Step 2, the coach yells, "You were 3 feet too high and a foot to the left." That's the loss function. It's just measuring how big the error was. But here's the crucial part, step 3. The coach doesn't just yell, they give specific advice. Lower your left elbow by 5 degrees. That is backpropagation. It takes the big general error and turns it into tiny, specific, actionable adjustments. So how in the world does the network become its own archery coach? Well, it does it with 3 core mathematical ideas that work together in perfect harmony. This is the engine room of the whole learning process. This is the machinery that makes that whole chain of blame possible. First up, we have the loss function. Now, that's a fancy name for a really simple job. It just measures exactly how wrong the network was. It looks at the network's guess, compares it to the right answer, and spits out a single number. The higher the number, the worse the mistake. So now we've got a score for our error. But a score isn't a solution, right? What do we do with that number? Well, that brings us to piece number 2, gradient descent. This is the algorithm that tells us how to make that error score smaller. Imagine our error is a giant hilly landscape, and our goal is to get to the very bottom of the lowest valley. Gradient descent is like a magic compass that always points in the steepest downhill direction from wherever you're standing. It points the way to a lower error. But it only gives us one single direction for the entire network. How do we turn that into tiny adjustments for millions of individual knobs? And this is the final piece of the puzzle, and it is the star of the show, the chain rule, straight out of calculus. This is the mathematical engine that takes that general downhill direction from gradient descent and figures out precisely how much blame each individual knob, each weight, gets for the final mistake. It works its way backward through the network, like a set of interconnected gears, telling us exactly how much to turn each tiny knob to help move the whole system downhill. Okay, so let's put all the pieces together. We have our loss function to score the mistake, we have gradient descent to find the general direction of the fix, and we have the chain rule to distribute that fix to every single part. Now let's see this machine learn. Because this isn't a one-time thing. It's a cycle, a constant loop of improvement. The learning cycle is basically 4 steps. First, the forward pass. The network makes a guess. Second, calculate error. The loss function tells us just how wrong that guess was. Third, the backward pass. The chain rule goes to work, calculating the blame for every single weight. And finally, fourth, update weights. We use gradient descent to nudge each of those weights just a tiny bit in the right direction. And then we do it all over again, thousands, sometimes millions of times.
This whole process really gets summarized in this famous little update rule. We take the old weight and we subtract a tiny amount. That little eta symbol is called the learning rate. It's just the size of our nudge. And we multiply that by its contribution to the error. To put it simply, if a weight pushed the final answer in the wrong direction, we nudge it back in the opposite direction. It's a tiny, tiny correction, but millions of those corrections add up to what we call learning.
There's this great saying in neuroscience that I think is a really good, if loose, analogy here. Neurons that fire together, wire together. And in a way, that's what backpropagation does. It strengthens the connections, the wiring between the neurons that were active when the network was getting things right, and it weakens the connections that led it down the wrong path.
Now, you might be thinking this incredibly elegant algorithm must have been this huge immediate breakthrough. But the story behind it is actually one of the most fascinating and kind of frustrating stories in the history of AI. This was a breakthrough that was literally forgotten for over a decade.
Get this, the core math for backpropagation was actually figured out way back in 1970 by a master's student in Finland. It was then described again in 1974. But for some reason, the AI community at the time just ignored it. It took until 1986, a full 16 years later, for Geoffrey Hinton and his colleagues to publish a paper that really showed off its power. And that's what truly ignited the deep learning revolution. The secret sauce was sitting right there on the shelf the whole time.
And once it caught on, the impact was absolutely massive. This one algorithm is the quiet workhorse behind so much of the world you see today. It's how the first practical neural networks learned to read handwritten zip codes on our mail. It's how your phone can tell the difference between you saying Martin and Marvin. It's even the engine behind the crazy process that creates those stunningly realistic AI-generated images.
And I'm not exaggerating when I say this. From the spam filter in your email to the most advanced AI models that exist today, backpropagation is the fundamental process that lets these systems turn their mistakes into knowledge. It is, quite literally, the learning engine of the modern world. And all of this leaves us with one last, really fascinating question. Backpropagation is an amazingly powerful and efficient way to assign blame and correct errors using the logic of calculus. It absolutely works. But is it how our brains do it? That link between the elegant math of artificial intelligence and the messy, beautiful reality of biological intelligence, well, that's still one of the greatest mysteries we're trying to solve.